G'day, United. How are you going? Today we're continuing our topic on measurement by looking at significant figures. Now, we would have mentioned significant figures when we were doing scientific notation early in the term, but we only brushed on it very briefly. Significant figures is a way of measuring precision. Basically, when you're doing a measurement, how precise you are in that measurement is very important for knowing how accurate and reliable your results are and how much can sort of be deduced from those results. So as a scientist, the number of significant figures that you use in your results is really important. There are all sorts of rules about when you're doing calculations, what significant figures you express your results in. These are also very significant if you're an engineer or if you're working in manufacturing, if you're making something. The precision that you make it to is very important, okay? Machines and making things usually have a tolerance value, which is basically a range of values which are accepted. And sometimes that tolerance can be very small, very precise engineering. So it's important that we understand the mathematics behind significant figures to understand these different fields and how the numbers work in those fields. So the number of significant figures that a number has is equal to the number of digits, including and between the first non-zero digit and the last non-zero digit. So that sentence is probably the simplest way you can say it. You're basically counting the digits between the first number that's not a zero and the last number that's not a zero. Okay, there is one exception to this, is that any zeros that are then after that last non-zero digit, but are after a decimal point, are also significant, okay, because they show precision. I'll talk more about that just in a moment. So in short, it's just we look at the first non-zero digit and we're looking for the last non-zero digit, okay? And then there is that other case, which we'll talk about in a bit, of zeros after the decimal point that we need to account for too. Okay, so let's do some rounding. Now, when we round, we use the same rules as, say, what you've been doing since year 7 with rounding decimals. So if the digit to the right of the place value that you're rounding to is 0 to 4, then you round down. That is the figure that you're rounding to doesn't change. And then if it's a 5 or above, then you will round up. That is, you'll increase the figure you're rounding to by 1. So when we're rounding to one significant figure, okay, I look at that first non-zero digit, which is a 6, okay, and then I look at the next one on the right, which is a 3, which means I don't have to change the 6 to a 7. I leave it as it is, okay, and then I need to show any zeros that are needed for place value. So what I'm going to do is I'm just going to write a 0 here for 60, okay. And that's all I need to do. I don't need to show point anything, 0.00 or anything, because those zeros are not necessary for place value. So I've rounded 63 point yada yada to 60. And there is one significant figure in that number I've rounded, okay? And that's the 6, okay? It's the first and the last non-zero digit. All right. For B, I'm going to 2 significant figures. So I need to look at what the second significant figure is. So 6 is the first, 3 is the second. And then I'm looking at the next one, the third one, which is a 7, which means I need to round the second one up. So this will become 64. And you can see there I have 2 significant figures, the 6 and the 4. They're both non-zero digits, so they're both significant. Okay. For C, rounding to 3 significant figures, I look at the third significant figure, okay, which is the 7. And then I look at the next one, the fourth one, which is a 5, which means I'm rounding up. So this becomes 63.8. Okay, and there are 3 significant figures there. It doesn't matter where the decimal point is, it's just how many non-zero digits do you have. So that's 63.8. Now, rounding to 4 significant figures, for D, okay, the 4th significant figure is the 5, and the next number, the 5th is a 0, so I'm going to round down, so it becomes 63.75. Okay, that's 4 significant figures. And then finally to 5 significant figures, the 5th significant figure is the 0, And that is a significant figure because it's in between the first and the last non-zero digit. So we include the zeros that are in between the first. If I have non-zero digits on either side of the zero, then the zero in between is significant as well. But in this case, that fifth significant figure of the zero, because the sixth one is a 9, it's going to round up, so it's going to become a 1. So 63.751 is that number rounded to 5 significant figures. Okay. So let's look at a few more examples here. So we have a number that was rounded to 2 significant figures. And we've got to work out what the smallest number it could have been before it was rounded and the largest number that it could have been before it was rounded. Okay, so we're starting to talk about tolerance here. What are the actual values that this number could have been before it was rounded? So for part A, okay, we need to think about what would round up to 430 if we're going to 2 significant figures. So if we had 425, okay, then that 5 would cause, if we were rounding to the second significant figure, that would cause the 2 to round up to 3. And if we had 424 or 4249 or anything like that, that would round down. So the smallest number that we can get is 425. And then the largest number that we could get, okay, is something less than 435. Okay, I'll put the less than symbol there. Because if we were equal to 435, it would round up to 440. Okay, so we could write 434999999 or 9 repeater. That would also be true. But in terms of statement, that also makes sense. And then for part 3, our mathematical statement is going to be, okay, we've got 425 as the smallest boundary, and our number, okay, we're going to call this number x, is going to be greater than or equal to 425. Okay, so it's greater than because it's on the great side of this symbol, and it could be equal to as well. But then that number has to be strictly less than 435. So it can't equal 435. So you've got this sort of asymmetry in that the number on the lower end is equal to or greater than, and then on the other one, it's strictly less than. Okay, so that's a mathematical statement that shows the possible range of values that our number x could be if it was rounded to 430. Let's look at this example here too. So this could, for part 1, we could have had 3.65. Okay, and then for part 2, it's got to be less than 3.75. And so the boundary is going to be 3.65. Okay, is less than or equal to x, which is strictly less than 3.75. Okay, so hopefully we understanding of what the range of the true value could be when we've rounded something. All right. So for this one, we're simply counting the number of significant figures, and we need to be watchful. Count all the non-zero digits, or the first non-zero digit, and count all the digits in between to the last non-zero digit. But then be careful about zeros after the decimal point. Okay, so the first non-zero digit is the 2. The last non-zero digit is the 4. We've got 3 significant figures here. The first digit here is a 0, so we don't count that. So we've actually only got 1 significant figure, okay, the 3. For C, this is where we need to be careful. So we've got a 4, we've got a 2, and then we have a 0, but that 0 is after a decimal point. So that actually is significant in this case because if we think about it, if I say 4.20, then you know that that could be anywhere between, so 4.195 or 4.205. Okay, that's the range of values that could be. If it was just 4.2 without the 0, then it could be anywhere between 4.15 or 4.25. So you see that 0 actually narrows the range of possible values that we can have, and therefore it is significant because it shows the precision of the number. So this has 3 significant figures. Now for this one, D, okay, we only start counting at the first non-zero digit. So even though these zeros are after the decimal place, we haven't had a non-zero digit yet. So they're just showing place value. They're not showing precision. So the first significant figure is the 1, and then the second significant figure is the 7. So we've got 2. And then finally here, we've got a 5, and then the last non-zero digit is the 6. And those zeros after the 6 aren't after a decimal place. They're not showing precision. They're just showing place value. So this has 2 significant figures. Okay, I hope good luck with the work today. I know first time, sometimes these rules can be a little confusing, but just think, is that 0 needed for place value? If I got rid of that 0, would it change the number? So for this last example, if I got just cut off a 0, would it change the place value? And the answer is yes. We'll go from 56,000 to 5,600. They're different numbers. So that 0 is for place value, not precision. If I cut off the 0 for C, 4.20, if I cut off that 0, it would just be 4.2. Have I changed the place value? No. So why is the 0 there? The 0 is there for precision. Therefore, it is significant. Okay, in B, 0.3, if I cut off that 0, okay, then I would just get 3. So that 0 is needed to show place value. So it's not significant. Okay, good luck with the work today. Let me know if you got any questions, and I'll see you later.